And okay, so hello everyone. So today we are very happy to have Amber Jachin Liu to give us a talk. So Amber is a fifth-year computer science doctorate candidate at the University of Michigan under the guidance of Mosharraf, and her research centers on resource scheduling and machine learning systems. Her outstanding contributions have been recognized by the Machine Learning and the System Rising Stars program in 2023. She holds a bachelor's degree from the University of Michigan and Shanghai Jiaotong University. More details can be found on her personal website. So the mic is yours.
Yes, thanks for having me. And in this talk, you can learn about how to design a large language model serving system that is able to handle more concurrent requests while also maintaining a high quality of experience. Or alternatively, we can say we save GPU resources during deployment. So even when the server capacity is temporarily exceeded, our approach ensures a smooth and satisfying user experience by aligning the system objective with user expectations. So this work has some real impact. So starting from last summer, our project has been adopted by some infra companies like Together AI and Databricks. And interestingly, last year around November, or before November, ChatGPT user interface didn't focus too much on user experience. Basically, it simply streamed the tokens at the speed of the server-side generations. So I'm not sure if you remember it, but this will lead to a lot of inconsistent experience where the response sometimes felt incredibly fast, but sometimes it seems stuck. So but after the November, in recent months, not only ChatGPT, but also other platforms like Gemini, Grok, they all have started enhance their user interface to deliver tokens smoothly, demonstrating the practical use of QoE-aware large language model serving. But this project is more beyond just user interface. It consists of system scheduling insight. So let's take a look at what we achieved this. So since the introduction of ChatGPT, which attracted 100 million users in just 2 months after its launch, large language model-backed chat services has become part of our daily lives. And this explosive growth highlights the importance of serving system in terms of its efficiency, user experience, and the cost. So in this paper, we will mainly focus on those human-involved large language model serving services, such as the customer service, virtual assistant, and chatbot, etc. So I know you may want to know exactly what is quality of experience mean in large language model serving, but let's go straight to the problem of existing serving systems. So here is a trace that we're trying to replay 1 hour slice of Burst GPT, which is a real-world large language model serving request trace. On VLM, VLM is one of the most widely used large language model serving systems. And on the bottom, we visualized the request arrival rate over 1 hour, and on the upper side, we visualize the queue lines, queue length of running queue or waiting queue over the time. And you can stop me if you feel there's any background missing, because I'm not sure. I skipped some of the background knowledge of large language model serving systems. But yeah, so as you can see over this time, 1 hour request window, that there's some bursty period and also there's some non-bursty period. So for this bursty period that the serving system is experience the request rate that is larger than its capacities, then you can observe that there will be a longer waiting queue here, because the server can only serve around 100 requests. But if the request rate exceed, then all those requests arrive later will be delayed and experience a long waiting time. And as also you can see from the other time period that when there's not many requests arrive, then the resources is very underutilized, and you can see this from the GPU memory utilizations. So we also report the average token latency and average time to first token latency during this 1 hour time period. So the average token latency is doesn't consider the initial wait, which is pretty good. Basically means every user could receive 20 tokens per second. However, on the like initial wait side, a user is expected to experience around 40 seconds. So this is not what we want, and this will lose a lot of users. So one option is to over provision more GPU resources so that during this peak period, you can serve more requests without letting them wait. However, this will lead to much higher operational cost. And on the other hand, for this time period doesn't have enough requests, you largely underutilize the resources that you have. So which is not what we want. But staying with the current plan will lead to worse user experience. That's also unexpected because we may lose our users because the long initial wait. So what we want is a better user experience. At the same time, we doesn't increase our operational costs. And before we talk about the solutions, let's take a step back and look at why all of this would happen in the real world large language model serving. First, I will talk about some motivations, and later on, I'll talk about the pinpoint of existing serving systems. So the first motivations comes from the bursty request load in real world services. First of all is the request arrival rate, as I visualized in the previous slides, that we trying to analyze burst GPT, which has contains a 4 months real world large language model request trace. And as you can see, indicated from this name, it basically indicates there's a lot of burstiness over this period, either within an hour, within a day, or within a month. So here is just a 12 hours visualize 12 hours request arrival rate, and vertically it's like for every is 12 hours, and horizontally is the 2 minutes intervals within each hour's request arrival rate. And the color indicated the red means a lot of requests arrived, and blue means there's no request. And as you can see, either horizontally or vertically, we observe a huge variance on the request arrival rate. And moreover, another bursty request load comes from the request context length variance. So basically, some background knowledge is that large language model serving system is usually memory bounded. So which means to serve each request, it consumes a certain amount of GPU memory. And this GPU memory consumption is proportional to the request context length. So here we're trying to analyze the statistics of those request context lengths. And this is also one famous request workload that people often use. And we're trying to plot the density distribution of the input length and output length. And as you can see from this tail distribution of input length, you can observe that some requests have extremely long context, which will consume much more GPU memories than other requests. So that means even though the request arrival rate is constant, it might happens that there's some request has extremely long context, and that will also fully utilize the server and maybe exceed the server capacities at some point. So here, this is the first motivations. Basically, it's kind of suggests that it's also almost impossible to accurately and dynamically provision the resources to handle those dynamically changing requests load in the real world services. And the second motivations is there's a mismatch between existing server's objective and what user actually expected. So what does it mean? So first, here is just some numbers about the token delivery speed that existing serving system can produce. So basically, you can think of where these numbers are all run on A100, but H100 can have much better performance. So you can think of you can easily receive 20 tokens per second on the user side, which is we argue that which is much more than what we actually needed or what actually can digest it within 1 second. So here we have some statistics of how this human needed like requirements on the token delivery speed. So on average, we probably just can digest 5 tokens per second. So you can see the gap between like what the serving system can produce and what actually a human needed. So to observe that there's excessively fast token delivery speed. It's like generating token faster is good, but it also give us more opportunities to work around this to like align the objective of existing server through like existing server's objective to like more user oriented. And why this imbalance happens, right? Oh, sorry, no. So here are more numbers about like why in addition to like a very good time token delivery speed, we also have to look at the time to first token latencies. So here we're trying to change the burst durations. So basically, I like burst durations means how many minutes that the server will undergo like bursty request arrival rate. So with the increase of burst durations, we can observe an increase of the initial wait, even though like the token delivery speed is perfectly good, it's above what user expected here. But we also don't want like average time to burst token to be excessively long. So as together, we can observe there's a mismatch between the server objective and the user objective. And why does this imbalance happens? And this is all because existing large language model serving systems, they adopt first come, first serve request scheduling, which means when server reaches capacities, all those requests that arrive later will have to be wait. And this leads to a head of line blocking problems. Here is this visualization, a toy example of how this will lead to a mismatch between user experience and server throughput. So let's say we have one server which can only handle one request at a time. And there are 2 requests arrive at the same time. So the server can only handle one request, which is the first user. So until the first request finish, it will not serve the second request. So it takes some time. As you know, like large language model serving is autoregressive. So it's autoregressively generate token for request 1. And then after it finish, then it goes to user 2. So this time to process the request 1 is like time to first token latency for request 2, mostly. And however, on the other hand, on the user side, generating like 20 tokens per second is way more faster than user 1 can digest. So user 1 is getting like excessively fast token generation, quick time to first token latency, while user 2 is starved. So that is not what we want. So here we propose this. Here are 3 contributions that we made. So first, we define quality of experience for time text streaming services, and then we design a quality of experience aware serving systems that design to optimize quality of experience. And we are able to serve more concurrent requests without additional resources. And you might wonder, what is text streaming services? So for these conversational AI services, by nature, it provides an interactive conversations by generating token one after another and stream them back to the user to be digested. So for this token by token streaming nature is akin to the frame by frame streaming nature of video streaming services. We call such services as text streaming services. And what is user experience means in text streaming services? And here are some examples for you, very, very straightforward examples for you to understand it. So let's say we submit a request. For non-streaming cases, so you'll wait for like, say, tens of seconds, and the chatbot immediately give you all the responses, and then you start digesting from the very beginning. So this is the non-streaming fashion. And on the other hand, there can be like delayed streaming, which means you submit a request, and then the chatbot will think for a while, and then think for few seconds and then output the results. And this is also not what we want, especially if the initial delay is super long. So ideally, we want a perfect streaming that immediately after you submit your request, you get a response, and the response will output the tokens at the speed that you can digest. So as you can see from these three different user experience that I just visualized, the later two, the first two does not align with a good user experience. And all those unexpected user experience can happen when the server is overloaded and is not well scheduled. So to formally define quality of experience based on what I explained previously, let's look at this figure. I'm trying to also visualize this. So this figure is the like a number of tokens received over time. And we will first define what user actually needed by this expected token delivery timeline, which indicated like the time to first token latency that a user can tolerate. And the slope of this curve means the token delivery speed the user expected. It can be a reading speed or listening speed. So we argue that for the request that is above this curve, basically the user never experienced any pause in the process of token streaming, then we say this is perfect QoE. However, for the request like token delivery timeline that's below this black curve, then we argue that this request fail to satisfy user experience. And in between request 3 and 4, we say that request 4 is more annoying because request 4 give less tokens in the early stage for the user to digest, while request 3 give like more tokens so user can have something to digest anyway in the early stage. So yeah, here this is just another very high level examples. In the paper, we have formally defined a formula for quantifying the QoE. The intuition is to quantify such QoE loss by measuring the gap between expected token delivery timeline and actual token delivery timeline, like as visualized by this arrow here. And the larger gap means worse QoE. So after defining the QoE, the next step is obvious. We need to design a serving system that optimizes quality of experience. So we optimize QoE through we call token level request scheduling. And the intuition is to prioritize requests that have not get enough services or is about to violate their quality of experience. And on the other hand, we will preempt requests that already receive lots of tokens that are enough for their users to digest. And therefore, we can save the system resources to serve other requests who need tokens more urgently. And this scheduling will only triggered when the server exceeds its capacities. And here is a concrete toy example to illustrate how our scheduler works. So we have two components. First is the GPU executor, which has a capacity, and this is a time horizon. And on the other hand, we have a user. This is a very important component I haven't talked about. So user side, we have a token buffer. Basically, it will withhold all those extra tokens and will stream these extra tokens to the user at the right pace that the user expected. So let's say like the server generate 20 tokens at a time, but the token buffer will withhold those tokens and only stream like 5 tokens per second to the user. So the user will not observe or feel any like scheduling behind the serving system. User will only see like the token streamed out smoothly. Okay, and here is some legend we will use later. So first, at the time 0, we have 3 requests arrived. And fortunately, these 3 requests can just fit into our systems. So as you can see indicated by the capacity, these three requests have different memory usage, but they can fit into the system. And here we just visualize the request one. So let's say at each time unit, it generates 2 tokens at a time. And the token buffer will decide to only stream out 1 token at a time unit, because it's expected by the user. 1. Okay, in the next 2 iterations, 2 time unit, the serving system will keep serving those requests 1, 2, 3 until there's at the T3, requests 4 and 5 arrive. So as you can see, the server is already at its capacity, so there's no ways to serve requests 4 and 5. However, requests 4 and 5 will require immediate serving because the user don't want to wait. So what we do is we're trying to see which request has the lowest priority. We will define the priority later on, but the intuition is that because request 1 occupy most of the server resources, based on the size, and also request 1, the user 1 got enough token to digest and has a lot of tokens is stored inside the token buffer. So we decide at this point, we preempt request 1 and serve request 4 and 5 so that user 4 and 5 can get immediate response instead of wait until like request 1 finish. So at time 4, right, request 1 is no longer getting more tokens. So you can see from the token buffer side, it's stream out tokens without getting more tokens. But it's good that the user will not feel any path in the middle because the token buffer is handling this complicated request scheduling behind the server. So at time T4, request 2 finish, which is good. It leave more space for us to schedule other requests. And at time 5, as you can see, like the user 1 token buffer is almost consumed up, and it's time to bring back user 1 request. Otherwise, user 1 will experience a pause in the middle. So at this time, we decide to preempt request 3. And another observation is you can see like the request priority is decreasing over time because it's getting more and more tokens for the user to digest. So it is fine for us to preempt request 3 at this point. So we preempt request 3 and bring back the request 1, which whose token buffer is almost empty. So, and then we can serve request 1 for another like 3 time unit. And throughout all those process, user 1 will never experience any pauses, and also request 4 and 5 get immediate services. So we basically satisfy more requests while we didn't increase our resource usage. I'll pause here to see if there are any questions.
Cool. Any questions from the audience?
Okay.
Yeah, you can type it in the chat if you don't want to speak.
Awesome. Hope this talk example is clear. So to revisit the intuition of this scheduling algorithm is trying to allocate resources for requests based on the QoE urgencies and the resource usage. So basically, we will define the priority later on. So this is actually very interesting, or also traditional scheduling problem, which is knapsack problem, right? We have a objective to optimize the QoE gain under the resource constraint, and the resource constraint corresponding to the knapsack size capacity, which is usually the memory capacity of the serving system, GPU memory, or it can be the compute capacity. But because existing like serving systems are mostly memory bounded, so I will skip the compute for now. But in the paper, we have discussed in details how this compute works within our systems, compute bound. And also item weight is corresponding to the request resource consumption, also in terms of memory and compute. And the item value, like by serving a request, like by putting a request into the bag, you can gain some QoE. But if you ignore some requests outside the bag, then you can also lose QoE. So that is the formulation of this rescheduling problems. And as I said, the item value is defined as the QE gain, and QE gain is related to both. Sorry, I didn't have prepared slides for that, but you can think it as of for a request that already get enough tokens, then the QoE gain of serving this request is very small. But for a request that is about to violate the QoE, which means that doesn't have enough tokens in their token buffer, then its item value is very high. You can gain some QoE by serving it right now. So here the solution for this knapsack problem in our paper, we just use the greedy solutions, whereas you calculate the value divided by the weight and set it as the priorities, and you schedule based on the priorities of each request. All right, so one last thing about the scheduling algorithm is that there is no free lunch. So you cannot just keep preempting requests back and forth in order to satisfy all the requests to QoE, right? So there is some overhead associated with every preemption that you incurred. And the key idea to just trade off this overhead is we trying to quantify the impact of each preemption towards all the ongoing request QoE. So basically, every preemptions, the whole systems, without further optimization, the whole systems might be stalled for a few milliseconds. And every ongoing request will be paused for a few milliseconds. So if this is acceptable, then we will do this preemption. If this few milliseconds or seconds stall is not acceptable for ongoing requests, then we'll decide not to do it. The good thing of this overhead is that usually the overhead is relatively small. Each based on like the number of tokens for the preempted request, the overhead is usually about 0.1 second. So it's corresponding to just few iterations inside the system. So it's usually acceptable, but in the extreme case, we will decide not to preempt. Okay, so last thing is to show some results. So also similar in our paper that we have tried we have tried different request dataset, which has different input and output lengths to comprehensively evaluate our systems. And also we use different models because different model will have different architectures, which may indicate different system behaviors. For example, multi-head attention, which is the most original transformer architecture, is very memory consuming. However, as for like GQA, which is group query attention, it consumes less memories. So this might not this may display differences in behavior for our algorithms. And also we use A100 for all of those models. And the request arrival pattern is something new that we introduced. So it's also based on one trace is there are two traits that we use. One is the real world trace from Burst GPT, and another we use a synthetic trace that we call cyclic burst load pattern. That is what we observed from Burst GPT that for real world large language model serving services, we usually will experience a period of burstness, and it's characterized by its intensity, which is the request rate at the peak, and also its duration, like how long this this peak will last. So this is something new we introduced because like either gamma distribution or other bursty distribution cannot capture such pattern. And later on, we will tune the intensity and duration, like this configuration, to stress test our systems. Okay, so finally, we will report not only our average QoE on the different bursty request arrival, but also the resource saving to achieve 95% QoE. And also, we will report like the number of concurrent requests that can be served compared to the baseline. Okay. The baseline is mostly VLM, but there are some others which is not quite important. It's not widely used anyway. So here's just a recap. So remember in the very first few slides, I have talked about the first come first serve will lead to a very long waiting queue during the peak minutes. And here is our performance. So we can observe from this queue length plot over the same 1 hour trace, we can significantly reduce the waiting queue length from like 100-ish to 30. Even though there are 30 requests waiting there, these requests is probably have enough token to digest, so it will not significantly affect the user experience. And we also report the average QoE and average time to first token improvement. We have reduced the initial wait from like 40 seconds to 3 seconds, and also improved the average QoE from 0.7 to 0.95. Another observation is that we can see here we only have like around 10 minutes that the server exceed its capacities. However, we extend this period longer, but because at this period the server is underutilized anyway, so we're trying to use like serve those requests with a longer time period. So this is a little bit trade-off, but essentially it's good that we'll also utilize the server further. And here are some breakdown results, and these two figures might better help you understand what the system are doing. So essentially for VLM, by the way, this is the accumulated number of tokens over time, and each line represents one query's token delivery timeline. So for example, this purple line means it waits like 90 seconds until it gets served. And this blue curve means this user gets immediate token served and finish way faster than it expected, which is the dashed line here. So for VLM, because it is using first come first serve request scheduling, so for requests that arrive later, it will experience a very long initial wait as indicated here. But because we are doing some preemptive token level scheduling, when we do this based on the resource consumption and the attend QoE, so we make sure that all the requests, we try our best to make sure that these requests get their tokens above their expected token delivery timeline. So on the user side, they don't experience any pauses. Yeah, and here are also some CDF of the time to first token delivery, yeah, and also QoE distributions. We perform way better than VLM. And here are more end-to-end experiment results. So basically, we're just trying to increase the duration of the burstiness or increase the intensity of the burst period, and trying to report the average QoE under different models. And we all performs better than the baselines. Yeah, and that is all for me today. I welcome any questions and discussions.
Okay, thank you. Thank you for the very interesting talk, and definitely this is a very useful, I guess, maybe including me, A lot of people are complaining about those things. I mean, how the existing system is serving the large language models, and your work definitely have a real world impact. Okay,
Yeah.
so any question from the audience? So you can feel free to type it in the chat or just speak up. Yeah, I can start with one question. So I see, for example, um, you're talking about, let's say, dynamically changing the scheduling of the different requests, this kind of reordering the request, and does that impact? So, for example, what is the batching technique used in the system? For example, is it dynamic or continuous, and how does your this NS impact the batching scheme?
Yes. So we keep adopt the continuous batching in large language model serving. So as you can see from this toy examples that this is actually just continuous batching. Um, as you can see, we batch 3 requests at the same time, and every time we generate 1 tokens for each request. Mm,
Okay.
yes,
So that's basically saying it's still continuous batching, but you can uh interrupt the generation of a certain tokens and bring in a new one instead of saying
exactly.
waiting for the original to end. Okay, I see. Uh
Yeah.
okay. Then we have a question from the chat. How much impact does Andis have on the throughput since you decrease the time to first token and increase the QoE?
That's a good question. I'm not sure like we included in the paper because like the throughput is as we mentioned, like throughput is super important in offline large language model serving systems, but in like online serving systems, uh, on one hand, you observe these are a lot of underutilizations. So when the batch size is super low, the throughput is very bad anyways. And also, as you can see from indicated from this duration of the uh, head of line blocking, we actually extended this period further, which means we've utilized the server for a longer time, which might it also indicated it's decreased throughput. But we argue that throughput is not the first priority in online serving systems. But definitely, we will incur throughput uh, reductions because of the overhead.
Okay. So, do you have an estimation of how much slowdown you could have in terms of the throughput?
Hmm, let's slow down. Hey, I let me check if I have the numbers, but if not, I can show you. Okay, seems not. Overhead. Mm. Mm. Sorry, I don't have like
Oh,
concrete
it's fine.
number
Yeah,
because
no
we
worries.
didn't measure it.
Yeah, we can chat about more details later. Yeah. So one more question from the chat. Uh, I will ask for the first one. I mean, the easier one. Is this paper publicly available to view? And of course, the answer is yes. I think that's
Okay.
archived. So later, I think the talk title is the paper title, right?
Yes.
Okay, so yeah, so oh yeah, you already typed it here. Oh, thank you. And the second question is compared to a brand X VLM, what would be the cost impact and hardware adjustment that would be necessary to implement this?
So first, for cost impact, I assume you're asking for like how many dollars we can save, right? So we have this number reported in our paper. Um, basically, um, mm, maybe we can just look at this figure. So basically, previously you can only serve like this blue line, like 75 requests, right? 70 around 75 requests. But if the request arrival rate exceeds, like then to handle all those leftover like around 100 requests, then you ideally you need to over provision the resources by 2. So that basically means you need to double your cost. On the other hand, if you look at our solutions, that even though we still have a waiting queue, but indicated by our like very high average QoE, that basically means we can almost handle all those requests without over provisioning. So basically, it means we cut the request by 2, the cost by 2. And in the paper, we report more concrete numbers about this, which is, I think, save up to 61% GPU resources, or alternatively handle up to 2.6 more requests concurrently. Yeah. Am I sharing the right screen?
Yes, now it's a paper.
Oh, great, great. Yeah. Second question is the hardware adjustment. There, we don't need to adjust the hardware, I think, because it can run on A100 or H100. Yeah, anyway, yeah.
Yeah. Okay, cool. So any other questions from the audience? So yeah, if maybe you're still typing, so I can come up with a question. One more question. So since you mentioned it's running on A100 or H100. So are these a multi GPU system or just a single CPU? A single GPU.
Yeah, it's multi-GPU because to host those,
Oh,
yeah,
yeah,
it's not. Yeah.
I see, I see. Oh, so even the 3.8 billion it's needed for a 4 800. The first one, I
Oh,
agree. Yeah.
yeah. Yes, the reason is actually weird because it supports 128K context length. So they have to reserve this many memory for 128K context length, even though you might not use it, but that's kind of a,
I see, I see. Yeah, that's why I mean, just looking at the model size doesn't look that crazy.
yeah, good catch.
Yeah, okay, we have one more question from the chat. So how did you preempt the request, or is it just a choice of what to add next to the continuous batching once current requests have generate one token each?
I see. So, how did I preempt the request? This is not something new that I this paper invented, so I didn't talk about that, but it's important to mention here. So there are two ways to preempt the request. So one is called swapping, another is called recomputation. So basically, swapping means because every request has its context length, has its KV cache, which basically cache some information about its context. So you can either swap this KV cache to CPU and bring it back when you decide to serve it again. This is called swapping, and another is called recomputation. Basically, you discard this request, but only remember the partial output of this request, and then you bring it back by just do another pre-filling of the request, which is recompute the request from scratch. Um, so that's why the preemption will cause overhead, no matter what mechanism you use. And uh, and the second question, it is not just a choice of what to add next to the continuous batching. It's actually proactively preempt the request in the middle of the token generation. Oh, but I think you are right. Once the current requests have generated one token each, if in that sense uh it is we are scheduled at the token level. Yes.
Okay, so it's like in that case, it's after like all the requests for all the current token for the current requests are down, then you decide whether you do a preemption, right?
Yes. Yes.
Okay. Yeah, I think you showed the nice curve of the recompute cost and the swapping cost. I think I remember that one.
Yes. Yes.
Yeah,
Yeah.
that's the swapping and swap out. And so my one follow-up question is that sorry, I have many questions because this is
Please.
very interesting. And what I think is that, for example, now if the DeepSeek definitely the rival of Meta somehow at this point, and
Mm,
it's coming up with MLA, which is the multi-headed latent attention. So that would drastically reduce the amount of KV cache. So if
mm.
you, I mean, in case you are able to, let's say, switch to the MLA, and what do you envision the preference between the recompute and swap?
I see. That's a good question. So the overhead not only depends on the hardware configuration, for example, like PCIe bandwidth or like, for example, the computation power on A100 and H100. So like H100, you probably will prefer using recomputation because it's way more faster. So all of this is can be profiled. Like in this case, maybe like you can see recompute is much slower, but in some other but more powerful hardware and more compute efficient architecture, then you probably choose recompute. But all of this can be pre-profiled, and you can decide what preemption mechanism to use in that deployment case.
Okay, cool.
Yeah.
Great. So is there any more from the audience? If no, probably I think that's the end of it. I don't think I should ask more questions. I'm asking too many already. So let's thank Jiachen one more time virtually. And I guess that's the end of the talk. Thank you so much. And hope
Thank
to
you for
see
having me.
you. Yep. Hope to
Yeah.
see you
Have a
next
good
time.
one.
Yeah, have a good
Yeah,
one.
yeah, yeah. Bye
Bye.
bye.